again, everyone. This is your chemistry time. The topic we are continuing is entropy. I hope you are ready with your book, pen, and calculators as we will continue with some calculations today as well. Now, for those students who might have missed the previous two lessons, don't worry about it. You can catch up on those lessons at this link that you see here. So take a snap or a photograph and you can check it out later. Alright. So far in this topic, we have seen definitions of entropy. We have also seen how entropy is affected by change in temperature and physical states, and hence predicted the values for the entropy change of the system. That is, going from solids to liquids to gases, entropy increases, or it increases when solids dissolve to form aqueous ions, or when the number of particles or moles increases, going from reactants to product side. We've also proven these predictions through calculations as well. Do you remember the expression we use for the calculation of entropy change of the system? Well, there it is. Right, so delta S system is equal to the sum of the entropies of the products minus that of the reactants, where you were given the entropy values and then you had to substitute to calculate a value. With calculations, again, we saw that with greater disorder, you have higher entropy as we predicted, and hence a positive value for the entropy as well. Positive value indicated entropy was increasing. I should remind you again that it's very important that you write the sign of the value, whether it may be positive or negative. And don't forget the units, the joules per Kelvin per mole, along with the answer. I also left you with a question to think about. Do you remember? Were you able to find some answers to it? Well, before we get to comparing answers, let's have a look at today's lesson objectives first. So, by the end of today's lesson, you will see why enthalpy changes alone do not control whether reactions occur, since endothermic reactions can occur spontaneously at room temperature as well. And we will do calculations involving enthalpy and entropy to see feasibility of reactions by calculating the entropy change of the surroundings using the formula, and hence use both entropy of the system and surrounding to calculate the total entropy change today. Right, the moment you have been waiting for, isn't it? Let's revisit the question I left you with last time around. So we talked about the reaction of sodium and chlorine to form sodium chloride, as you can see there, which is an exothermic reaction. But it involved a decrease in entropy of the system. Again, you can see by looking at the change in the physical states there as well. We also saw the calculation proving this, isn't it? Do you remember this one from last time around? There it is. So now the question was, how can a change in which there is a decrease in entropy of the system still be possible? Because this is a chemical reaction that definitely does occur. In other words, how can a change in which there is a decrease in entropy of the system still be spontaneous? How can a reaction that goes from disordered, a gas, to ordered, a solid product, be possible? Let's see if you've got this. To find an answer to this question, let's think about what we did in the previous class. For this reaction, we only calculated the entropy change of the system, isn't it? In order to predict the feasibility of a reaction, we must also consider what will happen to the entropy of the surroundings. Yep, that's right. Don't forget about the surroundings. But about the particles in the surroundings, what will happen to them? Well, what do we know about this reaction? We can see that this reaction is an exothermic reaction and therefore will be releasing energy to the surroundings. So what does that mean? What will this emitted energy or released energy do to the surroundings or to the particles in the surroundings? What do you think? Yep, it should definitely increase the randomness of the particles as they gain more energy, and hence the entropy of the surroundings increases. In other words, although there is a decrease in entropy of the system, the energy leaving the system increases the entropy of the surroundings. Now, if you didn't quite get that part, don't worry about it, because this is what we will actually have a look in today's lesson in more detail. But if you were able to come up with an answer along those lines, that's really good. Well done. Furthermore, remember this statement we saw in the first lesson? We talked about the second law of thermodynamics. Well, if you don't, here we go. It states that a chemical reaction tends to go or occur in the direction in which total entropy increases. What does this mean? This means it is in fact the total entropy which determines whether the reaction occurs or not, or the spontaneity or the feasibility of the reaction. Total entropy involves both the system and surroundings. So in today's lesson, we will see details of total entropy and entropy change of the surroundings. But first, you might have noticed I've used the word spontaneity a lot. Did you notice that? So what comes to your mind when you hear the word spontaneous? Or when I say a reaction is spontaneous? Or how have you used this word before? Have you used this word before? I'm hoping you are shouting out some answers here. Well, did you say sudden? Or maybe sudden change? Coolly occur? Or something happening unknowingly? These are some responses we've gotten before from students. Now let's actually see a proper definition of spontaneous, shall we? So a spontaneous reaction can be defined as a process that takes place without continuous intervention by us. Or we can say that it is a reaction which occurs on its own without any external influence. Have a look at this example. Freezing of water to form ice at minus 20 degrees Celsius. If water is placed in an environment of, let's say, minus 20 degrees Celsius, it will definitely turn into ice. And the reverse will not happen at this temperature, isn't it? Let's have a look at more examples of spontaneous reactions. Here we have an example of a ball rolling downhill. You don't have to do much, isn't it? Or have a look at this reaction between ammonia and HCl, forming ammonium chloride. Do you think we can reverse these reactions? If so, how do you think we can reverse these reactions? Think about it. So if you've said increase in temperature or heating, you're right. We can in fact reverse the reaction of freeze in the first example we took, or ice into water, by heating. Heating will melt the ice into water. Likewise, to roll a ball uphill, we will need to intervene, just picking up the ball and going up the hill, isn't it? Or tie it to something and pull it all the way up. The same way we cannot get ammonia and HCl from ammonium chloride at room temperature. So in summary, what all these changes is telling us is that the reverse process of spontaneous reactions never happen on its own. Furthermore, spontaneity does not tell us anything about how fast or slow the reaction is or the rate of the reaction. Often when we think of spontaneity or spontaneous reactions, we think these reactions happen really fast, just like that. However, it's not the case always. Just that it can happen or occur. Now, are all reactions spontaneous then? No, as you suspected. As you might have learned earlier, it is mostly the exothermic reactions that tend to be spontaneous, like combustion reactions. That is because they require less energy to occur. So let's have a look at this video clip that I'm going to show you to recall a little bit on this concept of exothermic reactions and enthalpy.
Every molecule has a certain amount of chemical potential energy stored within the bonds between its atoms. Chemicals with more energy are less stable and thus more likely to react. Let's visualize the energy flow in a reaction, the combustion of hydrogen and oxygen, by playing a round of crazy golf. Our goal is to get a ball, the reactant, up a small rise and down the other much steeper slope. Where the hill goes up, we need to add energy to the ball, and where it goes down, the ball releases energy into its surroundings. The hole represents the product, or result of the reaction. When the reaction period ends, the ball is inside the hole, And we have our product, water.
Now, if you can relate the hill to this diagram here, you can see that the reactions need to go up the hill and you need energy for that, shown by the small orange arrow going upwards, activation energy otherwise. And you can see the reactants go over the hill and then form products which are thermodynamically more stable or otherwise occupies a lower energy level than the reactants. This is a driving force behind many reactions and causes them to be spontaneous or occur without external influence. However, it is important to know that endothermic reactions can be spontaneous as well. Have a look at this example here. Solid hydrated barium hydroxide reacting with solid ammonium chloride, two solids reacting, occurs at room temperature in a rapid endothermic reaction. Here you can see, unlike the previous reaction, the products formed are thermodynamically unstable. And yet, this reaction is still spontaneous. In this reaction, entropy of the system is increasing. As you can see, two solids react to form a gas. But the reaction is an endothermic reaction, where energy will be absorbed, which will in turn decrease the entropy of the surrounding particles. So again, what actually makes this reaction to be spontaneous? In the previous one, the exothermic example, was it the enthalpy that drove the reaction forward? Or was it just the enthalpy? And here, could it be entropy of the system that is making the reaction spontaneous? Or could there be more factors? What do you think? Very important questions to think about. So what governs the spontaneity of a reaction? Well, it's not just entropy and it's not just enthalpy, but a bit of both that actually drives the reaction forward. As I have pointed earlier, both enthalpy and entropy is used to determine if a reaction is spontaneous. And as we saw earlier, according to the second law of thermodynamics, the total entropy always increases in the transformation of energy. Which brings us to our next objective of the lesson. What is total entropy? How is entropy of systems surrounding an enthalpy, all these terms, related to the total entropy? This is also where we will go further into some calculation. So let's have a look at what total entropy is. Right, so total entropy is denoted by delta as total. It is the sum of the entropy change of the system and the entropy change of the surroundings. And this is the expression we will use to calculate the total entropy. As you can see, it includes both entropy of the system and surroundings. And for a reaction to be spontaneous, that is feasible or possible, or for it to occur, now these are terms which we will use interchangeably. So for a reaction to be spontaneous, the total entropy change must be positive. So we need both entropy change of system and surrounding for this calculation. Right, since we have already seen how to calculate the entropy change of the system using this expression here, let's have a look at how to calculate the entropy change of the surroundings. So here we have the expression for surroundings. Minus delta H over T. You have to use the minus sign when you substitute the values. The H representing enthalpy and T for the temperature in Kelvin. Note that while entropy values are usually quoted in joules per Kelvin per mole, enthalpy changes are usually quoted in kilojoules per mole. So in any equation linking entropy and enthalpy, one of the energy terms will need a conversion of units. So what we will do here is we'll convert the enthalpy value from kilojoules into joules. That way we get entropy in its standard unit, joules per Kelvin per mole. To do this conversion, we can multiply the enthalpy value by 1000 in the formula and substitute into the equation so that our final answer will be in joules per mole per Kelvin. The entropy change of the surroundings will depend on temperature, but we will see those details in the next lesson. For now, let's try and work out an example to calculate delta S surroundings. Right, example 1, calculate the delta S surroundings at 298 Kelvin for this reaction shown here, and they've given you the enthalpy value as well. So similar to the calculations we did for entropy change of the system, we will work these out in steps as well. So first things first, let's write down the expression minus delta H over T, and then we go on to substitute the values. Right. Notice that the enthalpy is given in kilojoules, which means we will need to convert that into joules. Right. How do we do that again? By multiplying it with 1000. There we go. That's your next step. I hope you've got it all right there. Have you got an answer like that? 959.7. But don't forget the units and the sign. Very, very important. The sign, although it's a positive value, you must still write it down because it denotes something very important, isn't it? It's a positive value, which means just like the entropy of the system, entropy change of the surroundings is increasing. That is, while there was a decrease in entropy of the system, as you can see, two gases forming a liquid, the energy leaving the system increased the entropy of the surroundings. That is, since it's an exothermic reaction, the energy that is released to the surroundings will make particles in the surroundings gain energy. Therefore, there could be more ways in which these particles could be arranged, and hence more disorder. And you know what that means, isn't it? More entropy, and that is why entropy of the surroundings increases. Or we can say you will have a positive value. Let's stop and think. Could we have predicted that the sign would be positive without the calculation? Hmm? Have a look at the expression again here. Delta S surroundings is equal to minus delta H over T. And if we do the substitution and we have an exothermic value, a negative value, negative into negative, you will get, yeah, a positive value, isn't it? So even without calculating, we can predict the sign of the value once again for delta S surroundings, just like we did for system, and therefore you can suggest what would happen to entropy change of the surroundings, whether it will increase or decrease based on positive or negative value. The only thing we wouldn't know is just the magnitude of the value, isn't it? So this means for any exothermic reaction where delta H is negative, delta S surroundings will always be positive. So the entropy of the surroundings increases. Conversely, for an endothermic reaction where delta H is positive, delta S surroundings will always be negative. Therefore, the entropy of the surroundings decreases. I hope that's very clear to all of you. So now that we know how to calculate the delta S system and delta S surroundings, we're in a position to calculate the total entropy change of the reaction. So let's give it a try now with one more example, shall we? So example 2, here we have the formation of ammonium chloride, just like the small video clip we saw early on. Let's see if this reaction is feasible or not by calculating delta S total. To calculate delta S total, let's first calculate the system value. And before you calculate, you can even predict the sign of the value, isn't it? You have two gases reacting to form a solid. Entropy should decrease, yeah. So we would expect a negative value. But let's see if this holds true. Start with the expression. By now you should remember this expression here. Put in the values, substitute it, and see if you have something like that. Your final answer should be yes, a negative value, negative 284.5. Don't forget the units. Okay, so we've got the system. Let's try and calculate the surroundings now. So for delta S surroundings, we will also again start with the expression, which is minus delta H over T. And then before we get to the calculation, let's predict again what would be the sign of the answer. Your clue is right here. It's an exothermic reaction, which means minus into minus should give you, yeah, a positive value, which means we will expect entropy change of the surroundings to increase as well. All right. Now we can substitute the value, but notice again, temperature is given not in Kelvin, but in degrees Celsius. So how do we convert degrees Celsius into Kelvin? Well, you simply add 273. If you add 273 to 25, then you will get 298 Kelvin. Now that's an easy one to remember, isn't it? Because 298 Kelvin or 25 degrees Celsius is the standard temperature. All right. So let's put in the values. There we go. Just to show you how we got 298 Kelvin. Um, we are multiplying the enthalpy value, which is a negative value, by 1000. Why are we doing that again? Yep, because we need to convert kilojoules into joules, isn't it? Okay, I hope you remember that one. So what's the answer you're getting here? Is that the one you got? What are we forgetting here? Yeah, don't forget the sign and units. Very, very important. Plus 1055 joules per Kelvin per mole. So I hope that's okay to all of you. Just follow the steps. You should really not have a problem then. Okay, now we can calculate total entropy, isn't it? Right, so we've got the system and surroundings value. Let's just add the two values and let's see what your delta S total is. Yep, plus 770.5 joules per Kelvin per mole. I hope all of you were able to get that value. Since the total entropy is positive, we can say that the reaction will be spontaneous at this temperature. That means we will expect the reaction to occur at 298 Kelvin. That's very important to note here. As I mentioned earlier, the relationship between entropy change of surroundings and temperature, we will see details of it in the next lesson. Furthermore, we can say that although the entropy change of the system was negative, the entropy change of the surroundings was a large enough positive value, or the magnitude of delta S surroundings was greater to give a positive value for our total entropy. Which means it's important to note that the total entropy can still be positive even if one value is negative, depending on the magnitudes of the positive or the negative value. So I hope that's very clear to all of you. You have to remember the three formulas of delta S: system, surrounding, and total, and you should be able to predict the spontaneity of a reaction. So remember, for a reaction to be spontaneous, we have to consider both the enthalpy and entropy, namely entropy of the system and entropy of the surroundings. And those two gives us total entropy. When total entropy is positive, we can say that the reaction will be spontaneous. Remember, spontaneous means a process that takes place without continuous intervention by us, like the simple example of melting of ice at room temperature. And here we have the three formulas which you must remember in order to calculate the total entropy, and therefore working out if a reaction is spontaneous or not at that particular temperature. And we know for a reaction to be spontaneous, the total entropy needs to be positive, isn't it? And how would that be possible? Well, here are some scenarios. When you have delta as surroundings and system positive, you will definitely have a total that is a positive value. Reaction will be spontaneous or feasible. What about when you have two negative values, delta as surroundings and system? Well, simple mathematics, isn't it? You should definitely have delta as total a negative value, therefore reaction won't be feasible at all. What about when you have situation where delta as surrounding is positive and system negative, two opposite values? Well, in that case, if you need the total to be positive, therefore the reaction to be possible, then the magnitude of delta S surroundings need to be greater than the magnitude of delta S system. Similarly, if you have delta S surroundings negative and this time delta S system positive, then what would it be like for reaction to be spontaneous? Well, this time the magnitude of delta S surroundings should be less than the magnitude of delta S system. I hope that's very clear for you here. With that, we will conclude today's lesson. Hoping you were able to follow the concepts clearly, and in the next day's lesson we will look into how temperature can affect the feasibility or spontaneity of reactions, and this table will be quite important when we look back next class. We will also have a look at some exam style questions or past paper questions just to see how we can work along or do some practice. So once again, thank you all for joining in. Until next time, have a good day.